Hello, everyone. This is the Professor Ma, and these sections about limit. We study the tangent line, particularly we calculate the slope of a tangent line at a point x for these particular functions. And the way we do it is we did it by approximations, because I need 2 points to calculate the slope of a line. So we approximate the slope of the red line by go to another point on the curve and connect the black line, and we calculate the slope of the black line. And the slope of the black line can be calculated with symbol x and h, because I know what the curve is. So the difference quotients simplify, cancel the algebras, blah, blah. And I get the slope of that black line, the formula, depending on what x is, what x I chose, and how far the neighbor is the h. And I get the slope of that line depending on these two variables, x and h. And then we do the following things. We say we're going to let h become smaller and smaller and smaller, which is fine. Then we say shrink to 0. Okay. And conceptually, that's clear. So h shrink to 0 means h becomes nothing. And then the answer becomes 2x minus 2, which, if you think about it, it's the slope of the red line, because the black line will, as it goes along, the neighbor gets closer and closer, the black line gets closer and closer, and so we get the value of the slope of the tangent is 2x minus 2, depending what x is. Okay. And so this calculation is good, except we need to clean up the language. Particularly conceptually, look clear what we mean by we're going to let h shrinks to 0. We use these things, this language is called limit. Okay. So this is one way to conceptualize it. And the way in this one, we conceptualize through sequence. There's another way of doing it, to do epsilon delta, which is a continuous one, versions of these. So let me do these sequential versions of conceptually capture what we mean by limit. Okay. We can conceptualize what the infinite sequence is, okay? And we says the infinite sequence, when you're thinking about this one, is shrinking. 1/2, 1/3, 1/4, okay? In particular, they shrinking from the right-hand side, they shrink to 0, first of all. Secondly, they shrink to 0 on the right-hand side of 0. Right, so on the picture, it looks like this. We got these points going to these. Okay. So we define what we mean by a sequence shrinking to 0. For this one, it's clear that that it's shrinking to 0. But in general, how do we define a sequence shrinks to 0, goes to 0? The definition for a sequence goes to 0 is regardless how small of a neighborhood on the right-hand side of 0, that you take a little block a little interval to the right-hand side of 0. It doesn't matter how small the block, the interval is. Only finitely many of these x's you have in mind are outside the interval. Okay, you can shrink the interval even smaller. Still, only finitely x's are outside the even smaller one. Okay, if such is the case, we say the sequence goes to the 0 from the right-hand side. Then we says as x go to 0 from the right-hand side. Okay. Now notice there's no more index I anymore. We say as x goes to 0 to the right-hand side means for every conceivable sequence you can think of, that go to 0 to the right hand side. The following things happen. So if for every conceivable sequence, go to 0. Okay, you plug in the formula square root of x over x, and you look what the output is every time, and you find out every time it's 1, because given on the right hand side of the 0, absolute value of x is x. So if I divide both sides by x, x divided by x is 1. Okay, so therefore we say as x goes to 0 from the right hand side, the formula x absolute value divided by x goes to 1. And we're writing this manner. X, the limit x as x approaches certain numbers, the formula produces 1. Okay. Note is very important. I cannot plug in a 0 into this formula because it's undefined. Okay. On the other hand, if I do this to this formula, when x go to 0 becomes smaller and smaller, then 3x is 0 plus 2, then you get the limit 2. So conceptually, this is how we define something. X goes approach 0. The formula limit is conclusion blah blah 5, 6, 10, undefined. Okay. Similarly, I can talk about x coming from the other side, left hand side. Okay, now I think about a sequence -1. So yeah, I'm thinking about a sequence getting to 0, closer and closer to 0. But except this time it's on the left hand side, all negative. Okay, same thing. It doesn't matter how small a neighborhood you take over here, only finally of the x's are outside. Okay, another way to say it is almost all. That's how we mathematicians say it. If the almost all, that means only finitely many are exceptions. All the infinite many, the rest must follow whatever is so the description. That's what almost all. Okay, so that means only finally the outside, just about everybody is inside this little neighborhood. Again, regardless how small this neighborhood you take, of course, it's smaller the neighborhood, the more will be outside, but it's still finite. They still have to be finite. Okay. That's the point. Infinity has a lot of rooms, but notice in this case, if I look at the formula square root, absolute value x divided by x, now I get the answer -1. Why? Because on the left hand side, x is negative, so x absolute value is -x. If I divide by x on both sides, I wind up in -1 every time. So now the formula produces different answers depending on the x, the directions x comes in towards 0. But on the other hand, for this formula 3x plus 2, it doesn't make a difference. In 0, you're still going to get the limit 2. You don't get on the right hand side 2 or left hand side. No, you just get the number 2 as the output, as the limit. Okay. Then finally, if we drop the plus and minus the directions, if just x goes to 0, or xi goes to 0, means that the sequence might be jumping back and forth with positive, negative number. Okay, but the absolute value has to go to 0. So think about alternating sequence such as that. Okay, and notice in this case, the limit of this formula is undefined of the formula root x, absolute value of x divided by x, because the answers for these it's plus or minus. Everybody think of a different ways that the pluses and minuses jump. They get a plus one, minus one, plus one, minus one. But another one person think of another sequence with minus and pluses jumbled. There's no way you can predict the plus or minus. So therefore, this sequence is undefined. Therefore, the limit is undefined. But on the other hand, it doesn't matter how the sign is. When x goes to 0, this 3x plus 2 is still 2. X shrinks and then get nothing. Okay. So In a similar manner, you can think about x approach a from number a from right hand side, left hand side. So I'll leave that to you to read through these. You can just copy, basically paste the definitions, more or less. It is changing number from 0 to the position to a. That's all. Okay. So again, these examples is very important. This is absolute value. These examples demonstrate the importance when we talk about limit. Of x approaching something, we have to be very careful about which direction it comes. Okay, so and then in this case, we can come from a particular direction, the limit exists, but for another different direction, the limit doesn't exist, or something like that. Okay, and here are so we have a symbol for limit, the language to talk about it. So here are some of the rules on limits, and limit of constant functions is a constant. Okay, doesn't matter what x is, the output is always a constant. So limit x, so these x approach a, then limit x equal to a. When x get close to a, then it's a. Constant can be pulled out. Power. Okay. When x approach 25, square root of 25 is 5. So these are all obvious. In fact, okay, for polynomials, you can just plug in. For fractions, you just have to watch out the denominator is not 0. For every other places, you get exactly the same number that you plug in. Okay. So in fact, for every elementary functions, if you can plug it in, then the answer is the limit. If you can plug in a, if a is part of the domain, let me rephrase that. If a is part of the domain, you can plug it in, then that's the limit. Okay. Of course, the question is the rest of it. The trick problem is the other case. Okay. So for example, here's the square root of x. X goes to 0 from the right hand side, limit is 0. From the left hand side, you cannot take square root of negative numbers, so it's undefined. Now, talk about approaching infinity. With what do we mean by x, a sequence of numbers? So we're going to, the idea of approaching infinities, something goes to infinity. By the way, it's not a number. Infinity it's again approximations of something involving something getting bigger and bigger without stopping, okay, without upper bound. Think of the sequence 1, 2, 3, 4, 5. Okay, so this sequence, of course, marching toward infinity. It doesn't stop, first of all, and secondly, there's no upper bound. And I can think of a sequence 1.9, 1.9, 1.99. These are sequences are also getting bigger and bigger, and so on, but they're all smaller than 2. Okay, so this one has an upper bound of 2. Upper bound, because a roof, if you like. That's not very good. B-O-U-N-T. Okay, upper bound. But a sequence goes to infinity doesn't has an upper bound. Okay, and what do we mean by sequence goes to infinity? Well, that means it doesn't matter how big of an interval you can think of, all the way to the left hand side of infinity is. Okay, it doesn't matter how big the number n is. Only finitely many of the x's you're thinking of is within this interval to the left hand side. Almost everything beyond a certain point, they all outside, or almost all to the right hand side. That's the definition of a sequence going to positive infinity. So what do we mean when we say limit go to infinity, f of x, blah, blah, blah? Then it's for every sequence you can conceive of going to infinities, that such the following the statement behind it is true. So for instance, if x goes to infinity, I think of sequence going like then one of x goes to 0. It doesn't matter. Yeah. Oh, by the way, so they're all positive, by the way. That's what I meant to kind of remark on that. And similar, we can say from negative side, going to negative infinity, it's going to the left-hand side. Okay. And this shows up on the graph of 1 over x. Okay. We have a asymptote, a 0 where things go to infinities. And when x go to positive 0 from the right-hand side, the 1 over x becomes positive infinity. Therefore, you get a 2 asymptote on the graph. And then similarly, on the other side, when x goes to infinity, then when x goes to 0. And once positive was negative, so this is a positive, this is the negative one, and the 1 over x is very small. Okay. So this, it's positive negative side. Okay. Infinity, okay, but infinity is not a number. Okay, infinity is conceptual. It represents a sequence of numerical measurements that without bound. Okay. So, but we do have certain things, rules about infinity, the behavior of it, we can talk about. So here we go. Okay. If I know two formula goes to infinity, positive infinity, and one formula, that infinity plus infinity is going to be, the answer is going to be infinity. What do we mean by that is, so if when x goes to infinity, x goes to infinity, x squared goes to infinity. So if I add them, basically things gets bigger and bigger. So of course the sum goes to infinity. Okay. Infinity times infinity, similar idea. It gets bigger. Two number gets bigger and bigger. Okay. I want to make a remark over here. Okay. Very important, only for plus, not true for minus, and which we will talk about. Very important. And constant times infinities, and times number goes bigger and bigger, gets bigger and bigger. Okay. A constant divided by number become bigger and bigger, denominator become bigger and bigger. Okay, the top it's a constant. Or if I know the number is always smaller than something, a bound, if the top is bounded, then the limit will be 0. Okay, and the situation for that happens sine x and cosine x. Okay, these two formulas, when they are on top of something, we try to figure out the limit. Actually, this has a formula for it. This something like that is always less than or equal to 1. Okay, so the bottom is infinity, so then the quotient is going to be 0. Okay. If a base is bigger than 1, then taking power become bigger and bigger. If a base it doesn't change, but the power changes, become bigger and bigger, then the answer goes to infinity, But if base is less than 1, like think of 1/2. Okay, 1/2 is going to be, the other way around. 1/2 is going to be 1/2 squared. The more power you take, the number shrinks. Remember that. Okay, so these are true when we deal with infinity, limit as limit goes to infinity. Here is what's not true. Okay, these are examples. Here is what happens if I subtract two formulas, each one going to infinity. And I want to, so think of a sequence of number goes up, become go to infinity. Another different sequence of them goes infinity. I ask you now, subtract them term by term. Okay, and tell me something about the difference of the subtractions. It's a different sequence, right? And the answer is we don't know anything about it. There could be anything. Here's an example. Okay, when x goes to infinity, then these are obviously true. But if I subtract x by x minus x is 0. Okay, I cannot. This is going to be 0. Okay, and x squared minus x is going to be infinity. Okay, in other words, I cannot subtract the terms. I can arbitrarily make the difference anything I want. Okay, so in other words, for these type of limit problems, you have to change that subtraction problems into something else to deal with it. And we will do that later on. You'll see that. Another place which is inconclusive is if I have a fractions, think of a fractions a over b, and think of a sequence goes up, become bigger and bigger, but think of another sequence become bigger and bigger. And can we draw a conclusion? What does the whole what do the quotients goes to? And the answer is we don't know. For examples, okay, I know again, limit x is infinity, limit x squared goes to infinity. But if I divide x by x squared, okay, and this is what you think about, oh, this top goes to infinity, the bottom goes to infinity, so infinity dividing infinity. He says, wait a minute, why is this? It's 0 because this is 1 over x. Okay. But on the other hand, you know, if you just plug in infinity, say this is 1. Okay. So I get different answers. So plugging in, look, infinity over infinity, I will possibly get different answers. So in other words, I don't know what the answer is. So we have to change the infinity over to infinity, this inconclusive form, into something else. And we'll see that later. Okay. So that's it. And then, for instance, here's another problem. And it said that if I plug in x on top, I get infinity. Or plug in x on the bottom, I get infinity. So both are going to infinity. But we'll see that the limit of this is 3/5. Okay. Okay, that's it. Bye-bye. Close. Stop. What